And it's essentially built out of products of disks and circles according to simplices in a simplicial complex K. And those products of disks and circles are attached together and topologized according to the face category of the simplicial complex K. And the moment angle complex as a construction is just very interesting, sort of in and of itself. You can construct interesting spaces. They have all sorts of useful properties. But not only that, they can actually bring insight into spaces that we already know about and understand. And I just want to give some quick examples of these different moment angle complexes. So take K to be two disjoint points, then the moment angle complex that we get turns out to be the three sphere S3. But what's interesting about this is that by realizing the three sphere as a moment angle complex, we actually obtain this decomposition of it as the union of two solid tori over their boundaries. Now, that's not an obvious decomposition, not at all. So whilst S3 is a space that is already very well understood, I just want to use this as an example of one of these decompositions of spaces that we already understand very well. Now, not only can we have spheres, but the second example that I want to give is with K being three disjoint points rather than two disjoint points, and then the moment angle complex is this wedge of three spheres together with four spheres. And we can also, if we take K to be a square, this is one of the examples that George gave in the previous talk, we get the moment angle complex to be the product of S3 with itself. Now, what's interesting about these particular examples is that we've got a range of things here. We've got manifolds, we've got a wedge of spheres, which is definitely not a manifold. The first two examples here are co-H spaces. The third example is not. So the family of spaces, which is moment angle complexes, is huge. They can have all sorts of properties, and it's just a very large family of spaces. And most importantly, we have this combinatorial underpinning. Now, whilst that is quite elegant, and like I said, we have, for example, this decomposition of S3 into the union of two solid tori over their boundary, it's not just elegance. This sort of combinatorial data, or this combinatorial underpinning of the spaces, ZK, is actually incredibly fruitful. And we can gain insight into these spaces, and there are very, very many theorems which tell us all about these different properties of ZK, and I just want to give a sample of those now. So the first one is due to Hochster, Baskarkov, Panov, and Buchstaber. Now, this essentially tells us how to decompose the cohomology ring of ZK in terms of the combinatorics of the simplicial complex K. Now, one thing which if the astute observer might note is that if we look at this cohomology ring isomorphism, this second isomorphism which I give here, the left-hand side is this direct sum over subsets of the vertex set of these cohomology rings of full subcomplexes. Now, I've told you that this is a ring isomorphism, but it's not obvious what the product should be on the left-hand side here. And indeed, the product is something which is referred to, referred to or not referred to, depending on who you are, but the product is something which I refer to as the Baskarkov product. It's due to Baskarkov, and it's induced by the inclusion, which I note here on the bottom. Okay, so that's the first example. So we can decompose the cohomology ring. The second example is due to Denham and Suchu, and then separately Gerbich and Linton. Now, what this does is it actually characterizes those moment angle complexes which have non-trivial triple Massey products. And this theorem shows that they are actually characterized by the one skeleton of the simplicial complex K. And we say that these non-trivial triple Massey products exists if and only if the one skeleton contains one of 8 obstruction graphs, excuse me. I'm not going to give those graphs here, but this is really important. Massey products are really hard to calculate. And this theorem actually characterizes the existence of non-trivial Massey products entirely in terms of the combinatorics of K. Okay, and then we've got a third example, which is due to Gerbich, Panov, Theriault, and Wu. This is a theorem which I believe George also gave. And this is a nice one because it actually really highlights this interplay between algebra, combinatorics, and topology, and in particular homotopy theory. And these are sort of a priori unrelated properties. The one skeleton of a simplicial complex being a caudal graph, the face ring being Golod, the moment angle complex having the homotopy type of a wedge of spheres. These things don't have to be necessarily related, but this theorem tells us that in fact they are via toric topology and via the study of the moment angle complex K. And finally, for my fourth example, I want to give this theorem, this very nice theorem of Chi, or Chai, excuse me for my pronunciation, which says that the moment angle complex ZK is an n plus m dimensional manifold if and only if the simplicial complex K is an n minus 1 dimensional generalized homology sphere. Now, I'll give the definition of a generalized homology sphere later, but I'll just say briefly that it is essentially a homology sphere. Now, a homology sphere is defined to be a manifold which has the homology of a sphere. Now, a generalized homology sphere is a homology manifold which has the homology of a sphere. So that's what it is, and I'll give the definition properly later. This theorem in particular is of interest to us because manifolds exhibit Poincare duality. Now, when it comes to an investigation of duality, this result is of interest. From a homotopy theoretic point of view, manifolds are not necessarily the sort of right objects to be dealing with, because if you take any space homotopy equivalent to a manifold, so just take any manifold and attach disks, you've not got a manifold anymore, but this space is homotopy equivalent. So we sort of want to try and understand what a homotopy theoretic generalization of a manifold might be. And that comes in the form of a Poincare duality space. And essentially, these things are what they say on the tin. So a Poincare duality space is a space which exhibits Poincare duality. It's important to say here that when I say it's a space that exhibits Poincare duality, I'm not only talking about the existence of an isomorphism between the appropriate homology and cohomology groups, but that isomorphism actually has to be induced by the cat product. That's what a Poincare duality space is. Okay, so with that, and in view of Kai's result, a natural question can be asked, which is, does there exist a sort of analog of Kai's result for Poincare duality spaces? That is a sort of homotopy theoretic version of Kai's result. Can we characterize those moment angle complexes which are Poincare duality spaces as opposed to manifolds in terms of the combinatorics of the simplicial complex K? And that kind of brings me to what our two main goals here are, and what I'm going to be talking about today, which is that firstly, we hope to characterize Poincare duality in the moment angle complex and related polyhedral products. But more generally, we hope to compare and study interactions between dualities in these different areas: topology, algebra, and combinatorics. Okay, so I'd like to start with the cellular chain complex of the moment angle complex ZK. Now, this is the sort of the following is due to Panov and Buchstaber. We can essentially equip the moment angle complex ZK with a CW structure which arises from the embedding of ZK as a CW subcomplex of the M-fold product of the disk D2. Now, what we obtain by doing that is that cells of ZK can be expressed as pairs Ji, where J and I are both subsets of the vertex set M, where I is a simplex of the simplicial complex K. And then we get these cells are now in one-to-one correspondence with such pairs, these subsets of the simplicial complex K, where I is a simplex of K. Panov and Buchstaber also constructed a cellular diagonal approximation for the moment angle complex ZK, and this is really important because cellular diagonal approximations in general are hard to come by. For an arbitrary topological space, we know that they exist, but exactly what they are, we don't know. But in the case of ZK, we can construct a cellular diagonal approximation, as shown by Panov and Buchstaber, which comes from a cellular diagonal approximation for the disk D2. So we start with a diagonal approximation for the disk, where the restriction of this diagonal approximation to the boundary of D2, that is the circle S1, is also a cellular diagonal approximation. And expressing this combinatorially, we obtain something of the following form. Now, recall that I said that cells of the moment angle complex ZK can be expressed as these pairs Ji. Here, I'm doing this in terms of a diagonal approximation on the disk, but when we restrict, we get a diagonal approximation on the moment angle complex. We get a diagonal approximation of the following form. So you get that these cells, sort of after taking the diagonal approximation and applying it to one of these cells, we get something that looks like the below. Okay, so we have a diagonal approximation and we've expressed it in terms of the combinatorics of K. What we want to do is use this to get our hands on the cat product, and the cat product is what we need to study Poincare duality in these spaces, ZK. Now, for any CW complex, the cap product is given by the composition of these two maps. So we take cochains and chains of the space X, we apply the diagonal approximation to the chains, and then we apply the evaluation map after applying the diagonal approximation. This is just true for any CW complex X. Now, we already have our hands on what the diagonal approximation is in the case of the moment angle complex ZK. And using the above, we can actually give an expression of the cap product in ZK. So if we take two generating chains and cochains, which I've denoted by kappa j comma sigma and kappa j hat sigma hat, this is the sort of expression for the cap product. And we expand this bilinearly to get the cap product in general on the chains and cochains of the moment angle complex ZK. One thing which I should say, in the above, I've been talking about the evaluation pairing. And here, the evaluation pairing is defined to be 0 whenever I have a chain and cochain of different dimensions. In that case, you could say it simply doesn't make sense, but we're defining it to be 0 in those cases. Okay, so this is an expression of the cap product in ZK. Now, in fact, using this expression of the cap product in ZK, we can obtain a different or slightly unusual product for the simplicial complex K. We have an isomorphism of cochain complexes. The cochains of ZK are isomorphic to this direct sum over all subsets of the vertex set of the simplicial complex K of the cochains of these full subcomplexes K sub j. And the isomorphism is given by the following. A cell denoted by j comma sigma gets sent to the corresponding R. This should be sigma upper star, and this should be C upper star K sub j. This should be cochains rather than chains. It's all the same in the end because you can just dualize this isomorphism and you get the isomorphism on the level of chains. But the point is that we have this isomorphism. I'm not talking about the differential here, but suffice to say that there is an isomorphism of chain complexes, not just graded modules. And again, where K sub j denotes the full subcomplex on the subset J of the vertex set M. Now, given this isomorphism and observing that we have this cap product between which takes cochains and chains of the moment angle complex ZK and maps it to chains of the moment angle complex ZK, we have actually obtained via this isomorphism a product between the cochains and chains of these full subcomplexes of the simplicial complex K. Now, Fan and Wang in a work from 2016 refer to this as the excision product. And I should point out at this point that this product is not the cap product in the simplicial complex K. It's not the same thing. It's an entirely different product which works on the level of this this object here, the direct sum over all subsets of J of these chains and cochains of full subcomplexes of K. Okay, so we've obtained some product on the level of K via the cap product in ZK. Now, using that product, we can actually characterize a property of the simplicial complex K, known as, well, being a generalized homology sphere. So generalized homology spheres, simplicial complexes which are generalized homology spheres, can be expressed using this using this excision product. Now, I just want to give the definition of a generalized homology sphere. A generalized homology sphere is a space which is an n-dimensional homology manifold which has the homology of an n-dimensional sphere. And this is something which I said verbally earlier, but just to give it formally, that's what a generalized homology sphere is. You could say that it is a homology sphere, but that sounds kind of stupid. So what Fan and Wang did in 2016 is they actually characterized, in the case that our space is a simplicial complex, they actually characterized the property of a simplicial complex being a generalized homology sphere in terms of this excision product that we just discussed. So we have that K is a generalized homology sphere if and only if we see this duality exhibited on the level of full subcomplexes of the simplicial complex K. And that is in particular on the level of the reduced cohomologies and homologies of full subcomplexes and their complements. And this is very elegant because actually what it does, and it's very nice in terms of an investigation, again, into duality, because it actually expresses this generalized homology sphere property in terms of some sort of duality. Now, again, I just want to highlight here that this is, again, in the same way that the excision product was not the cat product, this is not Poincare duality. This is something entirely different. This is just a different sort of duality, and this is if and only if, this exists if and only if K is a generalized homology sphere. And actually, one should state that carefully that their result does not need this isomorphism to be induced by the excision product. It is in fact as a consequence of these isomorphisms existing that they are induced by the excision product. So I just want to state that carefully. Okay, and now we're ready to essentially state the result which we've obtained for Poincare duality in the moment angle complex ZK. We have that if K is a simplicial complex on M vertices of dimension n-1 with non-trivial cohomology, then the moment angle complex ZK is a Poincare duality space of PD dimension n plus m, that is the dimension of the fundamental class, if and only if the simplicial complex K is a generalized homology n-1 sphere. And in particular, I've just stated the result of Fan and Wang below, which is that if K is generalized homology n-1 sphere, that is if and only if we have these isomorphisms. Now, given some time at the end, let me just see how I'm doing for time at the moment. Okay, given some time at the end, I'll come back to a bit of a sketch of this, of the proof of this result, but I won't go into that now. And this isn't a sort of a useful result, and it fits into the known results in the following way, and it sort of highlights a certain interplay between different dualities in algebra, combinatorics, and topology. We have that the moment angle complex ZK is a Poincare duality space over the integers. I should have stated all along, by the way, that my coefficients are the integers. I'm not taking field coefficients, I'm taking integer coefficients. The moment angle complex is a Poincare duality space over the integers, if and only if K is a generalized homology sphere over the integers. If and only if the face ring is Gorenstein over the integers, and that is if and only if the moment angle complex is a manifold over the integers. What's important here is that we are seeing an interplay between these, again, a priori unrelated dualities in these different areas. I haven't mentioned the property of a ring being Gorenstein until now. It's not necessarily directly relevant to my talk, but just briefly, Gorenstein rings are a certain special class of Cohen-Macaulay rings, which exhibit a certain type of self-duality. Again, I'm not going to go into the details here, but you could say that as a module, one way of defining them is to say that as a module, a Gorenstein ring is isomorphic to its canonical module. And for Gorenstein rings, the canonical module always exists. Now, that's the algebraic specialists or people who are more experienced with this in the audience, but otherwise, don't worry about it too much. Just it is an algebraic property which can be, in the case of the face ring ZK, expressed entirely in terms of the combinatorics of K, as we see here, and this was proven by Stanley, that this face ring is Gorenstein, that is self-dual in an appropriate way, if and only if K is a generalized homology sphere. And this slots in with the result of Lee-Kai. Okay, now, given this result, one might wonder, okay, we now have a polyhedral product, which is the moment angle complex, for which we have obtained a duality result. To what other polyhedral products does this result extend? Does it extend? If to any, to what does it extend? But maybe it doesn't extend to any further polyhedral products. And that's what the sort of second half of my talk is going to be based on. To what other polyhedral product spaces can we extend our result? Now, it can be extended to some, and the first class of polyhedral products which we can extend our result to can be obtained via something referred to as a simplicial multi-wedge construction, occasionally referred to as the J construction in the literature, but not to confuse it with a different homotopy theoretic James construction. We'll stick to calling it the simplicial multi-wedge construction. And it's defined in the following way. So if you have a simplicial complex K, and you have an M tuple of integers where each of those integers is 1 or greater, then the simplicial multi-wedge of K on this M tuple J is a complex which sits on the vertex set described there, which is 1, 1 through 1 sub J1, all the way up to m sub 1 through m sub jm. And it's defined by declaring what the missing faces are. So you say that if you have a missing face of k, then the corresponding subset of the vertex set just given is a missing face of k sub j. Okay, I'm not going to go too much into the details of that because it's actually an example of a more general construction, which I'm going to introduce in a moment. But the following proposition is very important. Given a M tuple of disks and boundary circles of those disks, where the disks are of dimension j, 2 j sub I, and the boundary spheres are of dimension 2 j sub I minus 1, then the polyhedral product, and I should note at this point, by the way, that I realized actually earlier today that I didn't give the definition of polyhedral product in general. But luckily for me, my colleague George Simmons gave the definition in the previous talk. So if you missed that, essentially the polyhedral product is just like the definition that I gave of the moment angle complex, except instead of having D2 and S1 in each one of the M variables, you can vary the spaces. They can be whatever you want. So here we're allowing the spaces to be disks and disks and boundary spheres of different dimensions. Excuse me. Now, the point is that this polyhedral product, according to this proposition of Bari, Bandevsky, Cohen, Gittler in 2010, is the moment angle complex Z on this simplicial multi-wedge K of J, where J is this M tuple of integers J1 through Jm. Now, the key point of this proposition is that it allows us to express this other family of polyhedral products, which are not a priori moment angle complexes. It allows us to write them as moment angle complexes. And I'm not giving the theorem here, but we'll see the theorem in a couple of slides' time, which says that, in fact, this K of J, this simplicial multi-wedge, is a generalized homology sphere if and only if the simplicial complex K is a generalized homology sphere itself. What's important about that is that we obtain the result that ds to the K, this polyhedral product here, is a prime graduality space if and only if Z sub Kj is a prime graduality space, and that is if and only if K sub J is a generalized homology sphere, and that is if and only if K is a generalized homology sphere. So we have extended our result to polyhedral products where this this first entry can be a disk of any, let me get this straight. The second entry can be odd spheres, any varying odd sphere, and the first entry can be the disk which has that sphere as its boundary. Okay, now, as I mentioned, that simplicial multi-wedge construction is an example of a more general construction, which was actually given by Anton Eisenberg in 2013. And that construction is known as composition of simplicial complexes. And I define it here. So the composition of simplicial complexes, essentially what it does is it takes a simplicial complex K on M vertices, together with M other simplicial complexes, K1 through Km, and joins them together somehow. And we end up with a simplicial complex on the vertex set, which is the disjoint union of the vertex sets of the simplicial complexes, K1 through Km. And it's given in this way. Now, this is a sort of non-trivial construction, and it's slightly complicated, so I just give a few examples. Morally, the way to view, well, actually, I'll say that in a second when I come to the first example. Okay, the first example is the trivial one. If I have a simplicial complex K, and every single one of the K1 through Km is a single ghost vertex, then the simplicial composition of K with K1 through Km is just K. You just get K back, okay? Now, if K itself consists solely of M ghost vertices, then the simplicial complex of K with K1 through Km is the join of K1 through Km. Now, with that in mind, the way that you can actually view this composition of simplicial complexes is to say that it's a filtration between, at the bottom, the join of K1 through Km, and at the top, the full simplex on this vertex set, L1 union L2, blah, 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 union Lm. And what happens is, if K itself is empty, we just have a join. If K is non-empty, then we add in more simplices than what is given by the join. And that's exactly what actually this definition says. It says add in more simplices. Whatever simplices are not existing in the K1 through Km, we add them in to the join according to the simplices of K. Now, in the second example, we see how this actually recovers the J construction or the simplicial multi-wedge construction as an example. If we take each of these Ki to be the boundary of some full simplex of dimension Ji minus 1, then the composition of K1 through Km with K is just the simplicial multi-wedge construction of K with this M tuple J given as written there. And finally, to give a more concrete example, nothing so general, we say that, okay, let's let K be a simplicial complex, just the boundary of a triangle on 3 vertices. Then we get that the composition of K1 through Km is actually the boundary, the composition of K with K1 through K3, excuse me, is actually the boundary of a tetrahedron. So the boundary of delta 3. Okay, so exactly how does this composition of simplicial complexes sort of come into the polyhedral product picture? Well, it comes in the following way. So the theorem of Eisenberg in 2013 says, okay, let K and K1 through Km be simplicial complexes on the vertex sets M and L1 through Lm respectively. Then we have the following theorem. If in our polyhedral product we have a disk of dimension 2 Li and then the moment angle complex Z sub Ki, where Z sub Ki is on the vertex set L sub I, so that's where this K sub I and this Li are related, then this polyhedral product can actually be written as a moment angle complex. So we have that it is the moment angle complex on the simplicial complex, which is the composition of K with K1 through Km. Okay. So we've now written this more general class of polyhedral products as moment angle complexes, and we want to understand exactly when this simplicial complex, that is the composition of K1 through Km with K, when is that a generalized homology sphere? Well, again, we have the theorem of Eisenberg, which states that this composition is a generalized homology sphere if and only if the simplicial complex K is a generalized homology sphere, and each of the Ki is a genuine boundary of a full simplex. So that is the triangulation of some sphere of dimension Li for all I. So it's not enough that K and each of the Ki is a generalized homology sphere. We actually want more. We want that K is a generalized homology sphere and each Ki is the boundary of a full simplex. Now, with that, we can actually state a further extension to the result which we stated earlier about moment angle complexes, and it comes in the following form. We have that this polyhedral product, D to the power of 2 Li, with a moment angle complex Z sub Ki as a polyhedral product to the power of K, is a Poincare duality space if and only if both of the following conditions are satisfied. That is that K is a generalized homology sphere and K sub I is the boundary of a full simplex on the full simplex of dimension L sub I for all I. Now, what's interesting about this is that one may have asked earlier on, okay, we know that the the simplicial multi-wedge construction extends this result about duality. We know that, okay, well, if I have a simplicial multi-wedge construction and a polyhedral product on if I have a polyhedral product on some simplicial complex K, where I have disks and odd spheres, where I have a disk which is the boundary of such an odd sphere, then I know that this thing is a Poincare duality space if and only if the simplicial complex K is a generalized homology sphere. So we extended it to such examples. Now, realizing that the simplicial multi-wedge construction is actually a special case of this, or can be seen as an example of this composition of simplicial complexes due to Eisenberg, one may ask, okay, well, I know that this simplicial multi-wedge extends the duality result. What about other compositions of simplicial complexes? Are there other compositions of simplicial complexes which extend this result in the sense that we have that K is generalized homology sphere if and only if the polyhedral product in question is a Poincare duality space? And the answer is there are no further extensions of the result. That is that if we have a polyhedral product of this form, a disk and a moment angle complex, this is a Poincare duality space if and only if it is actually a simplicial multi-wedge construction on K with these Ki. Okay, and just as an example of how this theorem actually sort of can be applied, we have, okay, given a simplicial complex K on M vertices and some natural number N where N is greater than 1, one might ask whether the cone of the N torus together with the N torus to the K, this polyhedral product here, one might ask when that is a Poincare duality space. And the answer is that it's a Poincare duality space only in the trivial case. That is only in the case that K consists of ghost vertices, so that this polyhedral product is just the M-fold torus. There is no other way of cobbling together a Poincare duality space in this case. You can't somehow arrange the simplicial complex K such that a Poincare duality space is spat out.
Excuse me, Matthew, it's Tony.
Hi, Tony.
In this theorem here, where you've got dzk to the k there, it's actually true in a subsequent paper we wrote on realizing all these by Davis-Januszkiewicz constructions, that's homotopy equivalent to, in the strong sense, in the strong toric topology sense, that's homotopy equivalent to replacing that disk with the cone on zk.
Yes.
Yeah, in the strong sense.
Yes.
Yeah, okay.
Yes, yes. So yeah, that's right. Thank you. So in this case, I could have easily, I didn't have to write d to the 2li in this first, I'll say first variable, despite whether that's the right language or not. In this first variable, I didn't have to write d to the 2li. I could have written the cone on z sub ki. I just went with d2li because it sort of looked a bit more similar to the ordinary moment angle complex notation, but I could have easily written it as yes, exactly, yes. So
it's not obvious though that that's true.
Okay. So I could indeed have written, or perhaps I could have had an extra homotopy equivalence here to say that this is the cone. This can also be said to be the cone on Z sub Ki. And this is also a Poincare duality space if and only if K is a generalized homology sphere and each of the Ki is the boundary of the
it's sort of torus equivariantly homotopy equivalent. It's not just a simple homotopy equivalence, it's torus action equivariant homotopy equivalence.
Okay. Okay, all right, yeah. Thank you. Yeah, so yes, yeah, I could have easily, in the same way that I've written the cone on T to the N here, I could very well have written the cone on the moment angle complex ZKI here. Now, this is just one example of where Poincare duality essentially fails for such polyhedral products, aside from in the absolutely trivial case where K consists solely of ghost vertices, and this thing is obviously just the M-fold product of N tori. Now, I just want to remark in my last 5 minutes about some potential further directions of, I don't know, work in this area, which is that I didn't and I won't say much about the proof of the result. You know, a proof can be deduced from earlier slides, which is essentially that the cap product in the moment angle complex ZK corresponds precisely to the excision product in the simplicial complex K. And when you look at Poincare duality in the moment angle complex, that corresponds precisely to this duality, which doesn't have a name, but which Fan and Wang proved was the same as K being a generalized homology sphere. Now, this proof can be extended instantly to the case where instead of having S1 in each of the variables, you have Sn for any n. You don't allow the n to vary across each of the m variables, but you could have, for example, instead of a moment angle complex, D2S1, you could have a sort of so-called generalized moment angle complex. I should be careful with my language there. But a so-called generalized moment angle complex where you have D3S2. The proof can just immediately be extended, and the proof works the same way. However, this result, where you have even spheres, not odd spheres, but even spheres, and sort of the disks which those spheres sit as the boundary of, cannot be recovered from this method because of the nature of the proof which I used. So there's sort of this result is suggestive of for me at least, suggestive of a more general result, which is that polyhedral products, which are of the form connex x to the k, are Poincare duality spaces if and only if k is a generalized homology sphere and x is a sphere, a genuine sphere. That's something which I'm frankly nowhere near proving at the moment, but can be suspected by this sort of result. But for example, the case where x could be an even sphere is not covered here, and that's a sort of direction of future work. But
excuse me, Matt.
Sorry, Tony. Yeah.
Matthew, yeah. In a paper we wrote long ago, where we wrote the for a general moment angle, general polyhedral product, we wrote the product structure in terms of that ring structure on the cohomology of the full subcomplexes.
Yes.
One corollary of that, which was true back then, more corollaries of that, but one corollary of that is in the case of cone on x comma x, right, which you just mentioned, the ring structure of that is completely determined by the ring structure of D1S naught and the cohomology of X. Very explicitly.
Okay. Okay.
That you might find that useful in your computations.
Yes, possibly. One of the sort of potential hurdles with D1S naught is that S naught is not connected.
No, yeah.
So sort of that's why the reason that this all boils down to the so-called complex moment angle complex case rather than the real moment angle complex case is that the computations of the cup product in the real moment angle complex case are extremely complicated.
That's right, but that it comes down to understanding the links, and there's a recent paper of ours, very recent, up on the archive a few weeks ago, which shows how to handle the products among all the links that determine that.
Aha. Aha. Interesting. Is that yourself, Martin?
Yeah.
And, friend Sam. Yeah. Ah. Okay. Interesting. Well, I will have to look into it. That is not something that I had. That's definitely not something that I had registered.
Yeah, it's just up on the archive now. Okay.
Thank you. Yeah. All right. Well, I just to be clear, I will. I'll stop there. That's the end of my talk, and as I'm happily welcoming any further questions.
Yeah, it puts a bit of a damper on things when it all works only for products of boundaries of simplices and things, but in the general case, it's very nice work. Very, very nice work, Matthew.
Thank you.
Okay. Let's thank the speaker. Okay, thank you very much. Are there any other questions or comments? No. Okay. Now we have a break until 6:50 p.m. in Moscow time. The next talk in 20 minutes.
Thank you.
Thank you very much.
So it's a big pleasure and honor for me to see a lot of young technologists around. And this is a talk based in part on a joint work with Victor Buchstaber that we actually published last year. So maybe most of the talk I will discuss our approach to families of polytopes and the applications in toric topology. And I will also show the solutions to some problems which we stated in that work with Victor Buchstaber. So that will be some recent progress. And this talk is going to be like purely geometrical. So most of the time I will discuss polytopes and families of polytopes. And what we did with Victor is actually we used his theory of differential ring of polytopes and introduced some notations and terminology. And it helped us to obtain some geometric results and apply them in toric topology. First of all, I would like to recall some of the Buchstaber's theory of simple polytopes. It was developed in a series of papers due to Buchstaber, Yerochovets, Fenn, Karitsky, Volodin, and others. And the basic definition by Buchstaber is that a family of polytopes is just a set of combinatorial polytopes such that for any n, any positive integer, a subset of n-dimensional elements, n-dimensional polytopes, is non-empty and finite. Such a set is called the family of polytopes. I will introduce another terminology, generalizing this in a sense that a family will be called k-parametric or k-parameter if each element of the family is uniquely determined by an ordered k-tuple of non-negative integers. Like one parametric family will be called a linear family, and it's a family such that, for example, in each dimension you have one and only one polytope, like cubes, simplices, associahedra, commutative, and etc. If a polytope is determined by k parameters, such a family will be called k-parametric. And let me introduce some important types of families which will arise in toric topology. The algebraic direct families of polytopes is such linear families that, let's say, each element of smaller dimension is a face of each element in bigger dimension. So by inclusions of face into a polytope, it's a direct system of polytopes and face inclusions. A geometric direct family is such a linear family that it's algebraic, and moreover, it satisfies the following condition on nerve complexes. Kp means the boundary of the dual simplicial polytope. It's a nerve complex. So this condition simply means that a nerve complex of a polytope of smaller dimension is a full subcomplex in all nerve complexes of polytopes with bigger dimensions. That's not always true, because if you take simplices, that's a linear family, one simplex in each dimension. It will be an algebraic direct family, because a simplex is a face in all simplices of greater dimensions, but not geometric one, because nerve complex of a simplex is a boundary of a simplex, and it's not a full subcomplex in any simplex. But if you take cubes, then it will be geometric direct family of polytopes. You can easily check. Let me proceed with another definition from Buchstaber's original paper. The differential bigraded ring of polytopes. This means that you take n-dimensional polytopes with m faces of codimension 1, and generate a free abelian group, one generator for each simple n-dimensional polytope, Pn, with m facets, and the second gradient is m minus n. Then P acquires a structure of a differential bigraded ring by means of the following operations on polytopes. You can perform disjoint union of polytopes. This will be addition in this ring. 0 is an empty set. Direct product of polytopes gives multiplication, and unit is a point, zero-dimensional polytope. And finally, differential operator, differential D, maps a polytope to the disjoint union of its facets. Yes, D squared is not 0 in general. So that means that this definition, this terminology is non-standard one if you compare it to homological algebra definitions. But still, we would prefer to call this a differential ring, because the boundary operator is very important and it has numerous applications in toric topology. I'm going to introduce in this talk. So if you have a certain family of polytopes, then you can generate a subring in this bigraded ring of polytopes, just generated by all members of your family F. Then F is called a differential family or closed with respect to differential D or D family if, if it's closed with respect to the differential D. You perform differential on any member of the family F, and you obtain something which is generated by members of the same family of small dimensions, of course. And sometimes families are D closed, D families, sometimes they are not. And then if they are not closed under differential, you can sometimes make a union of sets of families such that it will be declosed. The smallest extension to a declosed family or D family will be called a declosure of such a family. And finally, we say that a family of polytopes has complexity k if its declosure exists and can be represented as a union of minimally k linear families, the minimum of k linear families. And the problem that we stated with Victor is to construct families of graph-associahedra of complexity k for any arbitrary given k greater or equal to 1. To do this, we apply some previous results we obtained with Victor concerned with geometry of moment angle manifolds. There's no need for me to recall moment angle manifolds and complexes definition, since they were already mentioned in this seminar several times. For example, in the talks by Steve and by George today. Our result is the following. Suppose you have an embedding of a phase and you have an embedding of a nerve complex into nerve complex as a full subcomplex. That's important, that Kf is a full subcomplex in Kp. Then the following diagram commutes. Now H1 and H2 are classical equivariant homeomorphisms, and Zf is homeomorphic to Zkf. Zkp is homeomorphic to Zp, as we all know. And the induced maps are induced by this phase embedding and simplicial subcomplex embedding, and their equivariant embeddings of a submanifold and a CW subcomplex. Now, if you have a flux, let me say that if you have a flux simple polytope P, then these conditions are satisfied because each nerve complex of each phase is a full subcomplex. You can easily check it. In general, it's not true. I'm going to show a counterexample in this slide. But for a moment, let me say that for any geometric direct family of polytopes, the sequence of moment angle manifolds forms a direct system of manifolds with respect to equivariant embeddings. And the sequence of the ecohomology rings forms inverse system of rings and ring epimorphism, because actually Zf will be a retract of Zp. And let me show this counterexample. Take a triangular prism. Then it has two types of faces, triangular ones or quadrangular ones. The triangular face gives you S5 as moment angle manifold, and quadrangular gives you S3 times S3. Of course, in the first case, it will be a retract, and the proposition above works. But in the second case, this will be not a retract, obviously, and the proposition, the conditions in the proposition are not satisfied because it will be not a full subcomplex. The boundary of a quadrangular will not be a full subcomplex. That fails. And now, after these general settings, let me turn to concrete examples. Let me turn to the families of two truncated cubes, nestohedra and graph-associahedra. They, as we know, they include one by one. So graph-associahedra are flag nestohedra, and flag nestohedra are two truncated cubes. So this slide shows you the construction I proposed in 2016 to obtain moment angle manifolds with high non-trivial massey products. You start with n-dimensional cube, and you cut off faces of codimension 2 only, starting from the cube, and in such a way that the Stanley-Reisner ideal can be shown as follows. So Vk, Vn plus k plus I, and some other monomials corresponding to the new face cuts. I will show in the next slide the three-dimensional member of this family, Q3. We denote this family of these two truncated cubes by Q. And we showed with Victor that this is an example of a geometric direct family of polytopes. Because these polytopes are flag, this simply means that Qn minus 1 is a facet of Qn. This is sufficient to show that it is geometric direct family of polytopes. And here is an example. So this is three-dimensional polytope, simple flag polytope, which is a member of my family Q. It is obtained from the three-dimensional cube by performing two phase truncations of codimension 2. This is edges. We truncate two non-adjacent edges. This is dual to the Baskakov example of 2003, the first example of moment angle manifold having non-trivial triple massey product in the lowest degree. And now, but this polytope is not, yes, these polytopes are in general not nestohedra. And Victor and I wanted to proceed with nestohedra examples. This is definition of nestohedra. So you take a building set on n+1 vertices, and nestohedron is a Minkowski sum of simplices. Each simplex corresponds to the set in a building set S. And a graphical building set is, you start with a simple graph gamma on the vertex set n+1, and each subcomplex consists of a connected subgraph in this building set. Then the corresponding nestohedron will be called a graph-associahedron. This is classical definition going back to 20th century, maybe middle 20th century, but this setting was made by Karen Devadis in 2006. And here are the examples: permutahedron, stellahedron, cyclohedron, or Bottaups polytope, and associahedron, or Stashev polytope. All nestohedra are Delson polytopes due to result of Andrei-Zelevinsky. This means that there exists a non-singular toric variety or toric manifold over any nestohedron. And Buchstaber and Volodin proved in 2011 that nestohedron is flat if and only if it has a realization as a two-truncated cube. Now let me show you some examples of three-dimensional members of these families. Three-dimensional permutahedra. All those stellahedra, all those can be obtained from a simplex by cutting off its edges, as you see. Cut off three vertices and three edges, you obtain a stellahedron. Cut off this, you will obtain cyclohedron and Stashev polytope. Now, how boundary operator works on these families? Well, by Fechner and Sturmfield's result, the boundary operator works as follows. It's a sum of the restriction polytope and the contraction polytope. Here are the definitions. So they are both nestohedra of smaller dimensions. And for example, we apply this and obtain boundary of permutahedron. It contains only permutahedra. This means that the family of permutahedra has complexity 1. And the family of stellahedra from this result has complexity 2, because its boundary is generated by permutahedra and stellahedra, by two families. So it's not declosed. Stellahedra is not declosed, but its declosure contains two linear families, the family of permutahedra and the family of stellahedra. Now, this is a family of flag nestohedra that we introduced with Victor. Suppose you have the following connected building set on n+1 vertices. It's a union of the following subsets. All singletons should be members of building set by definition. Then 1, 2, and other subsets on bigger vertices, and 1 and subsets on bigger vertices starting with 3. That's how it can be represented. And if you perform the definition, you apply the definition of nestohedron as a Minkowski sum of simplices, you obtain flag nestohedra P mass of dimensions n, and this family will be called P mass. Mass stands for mass C, actually. I will show result in a few minutes, but now this is a picture of three-dimensional P mass. It's combinatorial equivalent to my Q3, but it looks affinely it's different. It's different affine embedding, but it's combinatorial equivalent. In general, they are not combinatorial equivalent with Qn. Now we would like to analyze the differential, how differential performs on these families of nestohedra. To do this, we should introduce a family of graph-associahedra, such that the graph is, you take a complete graph, and you take an edge alongside between vertices n and n+1. Then this will be an n-dimensional polytope called P gamma n. This P gamma n is also a nice an important family in toric topology. I will show its applications in a few minutes. But now this P gamma n has the following value of the boundary operator on it. The boundary operator sends it to the family of commutative, P gamma itself, and that's it. So complexity is 2, commutative and P gamma only. So P gamma has complexity 2. And now P mass in the boundary contains stellahedra, P mass itself, P gamma, and stellahedra. It means that complexity of P mass is 4. So we obtained a family of graph-associahedra P gamma of complexity 2 and a family of flag nestohedra P mass, which are not graph-associahedra, it can be shown, and has complexity 4. Well, so now I'm going to answer the first problem we stated with Victor last year. That was about arbitrary complexity linear families. The construction is as follows. Suppose you have 2 complete graphs. Then take their union alongside a vertex, and this will be a graph. So you take one complete graph, another complete graph, and glue them along one vertex. This will be a simple graph, and its graph-associahedron I denote by P of n1, n2. This polytope will have obviously dimension n1 plus n2. This construction is symmetric, of course, because you can interchange those 2 complete subgraphs. The initial conditions, as Victor prefers to say, is Pn0 and P0n is commutahedron, and Pn1, P1n is P gamma. And furthermore, this will be definitely a 2-parametric family of graph-associahedra, because each polytope is uniquely defined by 2 parameters, n1 and n2. Now, analogously, another construction, you take a complete graph, and the second graph is a path graph. Take a glue them in one vertex. This will be a simple graph gamma, and PA of n1 and 2 will be the corresponding graph-associahedron. Clearly, again, it has dimension n1 plus n2, and initial conditions will be it contains associahedra on the one side, and it contains permutahedra and P gamma on another side. So furthermore, it's also an example of a 2-parametric family of graph-associahedra. Again, it depends now not only on dimension, but on n1 and n2. Let me give the boundary values. The values of the boundary operator D contains, you see, permutahedra and the members of the same family. But permutahedra are also members of this 2-parametric family, as I showed on the previous slide. It's just initial condition for this. So we obtain that this is a declosed family. So it's closed with respect to application of differential operator, of the boundary operator. And regarding PA, it is also a D family. It is also closed. As you can see, only PAs here of smaller dimensions. It is also closed with respect to the differential operator. Now, here is the solution to the open problem about arbitrary complexity. From starting with PE2, this double complete graphs, first of all, it's a differential or declosed family, geometric direct family of polytopes of infinite complexity, because itself it has infinite complexity. But we can construct another linear family, f of k, depending on one parameter, k, such that it has complexity k. Since its declosure is simply f1, f of 1 is permutahedra family. Then f2 union with f3, etc., until up to fk. These are k linear families, so the complexity by definition is equal to k. K is arbitrary positive integer. Analogously, using PA2, the mix of permutahedra and associahedra, you obtain a differential geometric direct family of polytopes of infinite complexity, absolutely similar. And the linear family, depending only on parameter k, has complexity k for each k positive integer, since the closure is again g1 plus g2, etc., plus gk. This is the solution to the one of the problems we stated with Victor. And now let me go to applications in toric topology, because our main results with Victor, applies this theory to finding families of nestohedra with non-trivial massive products in cohomology of moment-angle manifolds. In Steve's talk and in George's talk, there was mentioned the massive product, and I think Steve gave definition for triple massive products, but we need higher massive products, and here is the setting which goes back to the times of Massey's original paper of 1958. Then Peter May determined matrix massive products and generalized the original concept. And we use the terminology going back to Babenko and Taimanov paper of 2000. Namely, we use the concept of defining system. It's a matrix times k plus 1, k plus 1, with the following conditions. It's an upper triangular matrix. On the first diagonal stands the representatives of our cohomology classes. And the third condition determines some certain cocycles A, depending on the matrix C, of course, such that their cohomology classes, by definition, will be elements of a massy K product of alpha 1, alpha K. This bracket is a multi-valued function. It is defined if there exists a defining system for it, and if so, it consists of all such cohomology classes for all among all defining systems C. This product is called trivial if it contains 0 element, and it's called strictly defined or uniquely defined if it contains the only one element. Let me give you examples. So a twofold massive product is up to sign just a product of 2 elements in differential graded algebra. A triple massive product, which was already defined by example, can be defined if 2 consecutive products are trivial. Then it's defined by this formula. And for example, fourfold massive product, you need all consecutive subproducts be trivial and degenerate simultaneously. That means that there is a defining system. Then it's defined using this formula. This will be a cocycle, and all such cocycles form cohomology classes in the fourfold product. And around 2002, the following question was asked. Buchstaber and Panov asked, does there exist a simplicial complex with a non-trivial triple or higher massive product in cohomology? I mentioned Baskakov, and he was the first to obtain an example of a non-trivial triple massive product. So we will see that P mass family, Q family, and P mass family gives us examples when there exists a non-trivial, uniquely defined n-fold massive product in cohomology of moment-angle manifold. Namely, my theorem was the first one that showed that in cohomology of a moment-angle manifold, there exists an arbitrary high non-trivial massive product. Moreover, it's uniquely defined. It contains only one element. And this enabled Buchstaber and myself to introduce the following definition. We call a direct family of polytopes a direct family with non-trivial massive products if there exists a non-trivial massive product in cohomology of ZPN with the order tending to infinity as the dimension of polytope tends to infinity. That's non-void definition because of the previous theorem. The Q family is such a family. Moreover, it's called a special family if for any dimension n, there exists a non-trivial uniquely defined k-fold massive product for all k between 2 and n. So let me show you our main theorem. We showed that the family Q, which I introduced in 2016 and worked out in 2017, is a special geometric direct family of 2 truncated cubes with non-trivial massive product. Since we previously showed the geometric direct family polytopes, that means that Qn minus 1 is a member of a facet of Qn. So by the previous proposition, the first one I showed in this talk, Zqn minus 1 is a retract of Zqn. That means by Buchstaber-Panov-Baskakov theorem that the massive product in Zqn minus 1 cohomology is contained, is mapped to by this split epimorphism to the cohomology of Zqn. and using multigraded structure, it remains to be non-trivial. And this shows the first item. The second item, P mass, is a special geometric direct family of plug nestohedra with non-trivial massy products, can be shown analogously because, as we saw, the boundary operator gives you all the facets of Pn mass. Among these facets, you have Pn minus 1 mass. So by induction on the n, if you showed that Pn mass contained n higher n non-trivial n-fold massy product, then Pn mass also contains all orders of non-trivial massy product from 2 to n. That's the application of the boundary operator and the theory of the direct families of polytopes. And so this theorem enabled us to state the following problem. Find special geometric direct families of graph-associahedra with non-trivial massy products. So is it possible to make the same statement for graph-associahedra? Well, recently there was a paper appeared in the archive by Yellen and Abi, who showed very nice results about higher non-trivial massy products with non-trivial indeterminacy, first of all, and they also analyzed some families of plug nestohedra, and in particular they analyzed permutahedra and obtained that there exists a non-trivial uniquely defined k-fold massy product in cohomology of moment angle manifold corresponding to n-dimensional permutahedra. But then it means that by means of our results, n-dimensional permutahedron moment angle manifold contains all non-trivial massy products of all orders from 2 to n in cohomology of moment angle manifold. Moreover, if you consider P gamma and the boundary operator on P gamma, then this polytope will also contain all the non-trivial massy product of all orders from 2 to n because of the value of the boundary operator. F of k and g of k are also such families. All in all, we obtain that permutahedra, P gamma family, F of k and g of k are special geometric direct families of graph-associahedra with non-trivial massy products. So this is also an application of the theory of two-parametric families, because F of k and g of k were linear families, obtained from two-parametric families F, P2 and PA2 of graph-associahedra. And let me finish with reminding you a very nice result of Alexander Gayfulin, who obtained the following in, I think, 2016, at least in the archive. He posted the following result. For any connected simple graph gamma, the real moment angle manifold corresponding to the graph-associahedron P gamma is a URC manifold. This refers, URC means universal realization of cycles, and this refers to the classical problem of Steenrod of 1940s of realization of cycles. URC means that it's such a manifold that for any topological space and any n dimension, if it has dimension n, then for any cohomology class of dimension n in any topological space, this class can be realized by mapping this manifold to that space and taking the fundamental class of the homology fundamental class of this URC manifold and mapping it to the homology of the topological space you take. So either this manifold or its finite fold covering will give you the class up to, of course, as in Thom's solution, for example, up to multiplier. Up to multiplier, positive multiplier, you will have this homology class. Such a manifold is called URC manifold. Alexander proved that for any graph-associahedron P gamma gives you a URC manifold as a real moment angle manifold. So this is another side of applications of graph-associahedra, and of course of all families we discussed today, because all such families give you families of URC manifolds. Families of URC manifolds. And let me recall finally that RP has dimension n, where n is dimension of the polytope. So RP gamma has dimension n if gamma is on n plus 1 vertices. So, and if we have families of graph-associahedra, that means you have families of manifolds, one manifold in each dimension. So this is another side, another possible geometric application of topological application of the theory of families. Here are some papers, starting with the very first one, where I obtained this first result on non-trivial high mass products. Then I generalized my constructions in my two subsequent papers in 2017 and 2019. And here are our publications and preprints with Victor, where we stated these problems we discussed today. And you can find all the necessary terminology and constructions that I had to omit because of lack of time. Thank you very much for your attention.
Thank you. Let's thank the speaker. Are there any questions or comments? Okay, maybe I have one question. Ivan, you said that there is a differential ring of polytopes, yes?
Yes, yes.
And of course, d squared is not 0 because it's just union of faces of codimension 2, yes?
Right, like and of course, if you perform
yes. But I think that maybe if you have something like orientation that
yes,
it's maybe 0 squared, and does it have some sense? Or
absolutely.
Maybe homology or
absolutely. Thank you very much, Gosha, for mentioning this. This actually is another problem still open now, which was asked by me and Victor in the same paper published in Izvestia, and you can see it in the archive now. The problem is such. So you can slightly change the definition of our D, make it, let's say, D prime. D prime is the same sum of all facets, but taken with induced orientations. Then if you take all the facets with the induced orientations, let's say the normals are outward pointing normals, then d squared will be 0, as you pointed out. And that means that you have not only a differential ring, but actually you have a differential such that you can define homology. You can define homology of polytopes of this maybe groups or rings of polytopes, of course, not just polytopes, because polytope geometrically is trivial, but this structure gives you something like differential graded algebra. So you obtain homology, and the question we posted is, well, let's compute at least in smaller degrees, in smaller dimensions, what is this homology groups? And I think there are some partial results for H0 and H1 obtained by one of the students of Victor, but maybe still unpublished. I'm not so sure about that. So we could not even mention those in our paper, but well, only some partial results. So it looks like non-trivial problem even for smaller dimensions, but we have no general formula at all, no idea about general formula.
But some sense of low dimensional homology of 0 homology. Okay, thank you.
Yeah, so well, 0, yeah, you can consider all, yeah, you can consider all segments. Yeah, segment is the only one-dimensional simple polytope, and then yeah. But then you have polygons, and depending on parity, you know, it can have different values and so on and so forth. So you can compute maybe zeros and first homology. It will be a nice result. But then already second homology, I have no idea how to compute. Yeah, but that's a very geometric and clearly it's an open problem. Very nice problem, I think.
Okay, thank you.
Yeah, thank you.
We have a break until 4:40 p.m. in Moscow time. The next talk is in 14 minutes.
Here, and first of all, I would like to thank the organizers for inviting us all here. It was a very nice conference. So today I will talk about computation of basic homology of complex manifolds with maximal torus action. And so the plan for today is, first I will introduce these manifolds and speak a little bit about them, then pass to the computation. Okay, so M complex manifold, well, here it's not necessarily even complex. So it's called the manifold with maximal torus action. There exists some compact torus G, which acts effectively on M. And also there exists some point X in M such that the dimension of G plus the dimension of the stabilizer is equal to the dimension of the whole manifold. Well, it may seem like a little bit strange condition, but this condition guarantees us that this torus is a maximal torus acting effectively on M, in a sense that there is no other compact torus G prime such that G sits inside G prime and G prime acts effectively on M. So this is not a very hard claim to prove. So I would like to introduce the category of such manifolds. And at the first glance, it seems like quite a general property, but actually all these manifolds have constructive description, to which I will pass later. So C1 would be the category of complex manifolds with maximal torus action, and the objects of it are triples of M, G, and Y, where M is a complex manifold, G acts on M as in this definition, and Y is some point such that the stabilizer of Y is trivial. So, namely, the orbit is the open orbit of this point. And the morphisms in this category between two such triples would be pairs F and alpha, where alpha is a group homomorphism between these compact toruses, well, smooth. And F is a map from M1 to M2, which is alpha equivariant. And we also require that the image of the point F Y1 is equal to Y2. So actually from this definition, it can be seen that it doesn't matter which point in the orbit you choose. But this definition is definitely not constructible. So I will introduce another category, which actually weak equivalent to this one. So, well, we will think now of G as of T to the power M, and with this Lie group, there is associated map from exponential map from its Lie algebra to itself, and Lie algebra is simply real m-dimensional space, and the kernel of this exponential map can be we can think of it as of a lattice, and it's isomorphic to z to the power m. We also consider the complexification of this Lie algebra G, which is isomorphic to c to the power m. It can be decomposed as a sum of G plus Ig, and we would denote the projection to the part G as a real projection and denoted by RE. So the objects of this new category C2 would be triples of some fan, some linear subspace in GC, and G itself. So sigma is required to be non-singular rational fan in G, where non-singular means that it's this is a rational fan with respect to this lattice kernel exponential, and non-singular means that all the cones are generated by part of a basis. So it means that the associated toric variety is smooth. Okay, H is a subspace which is required so for it, it's required that its projection on the real part is injective. So it means that it transversely intersects the real part actually. And we associate with this complex subspace a map Q from G to the quotient by this projection on real part. And this real part I will denote later by H prime. And we want the image of a fan sigma under this projection to be a complete fan. And this is actually very put many restrictions on the possible fans that could appear here and their relation with dimension of H. And we want also the map to be bijection between the fans, the cones. So the morphisms between these objects of this new category would be the maps from G1 to G2, such that the alpha, which sends the algebra G1 to G2, sends also plays a role of a morphism from a fan sigma 1 to sigma 2, and we also ask the alpha to send H1 inside of H2. Well, then how to go from the category C2 to the category C1? Having this triple, we associated to it the manifold, which is equal to V sigma quotient by H, where H is exponent of H, and it sits inside of a compact of a algebraic torus since H sits inside of GC. So this algebraic torus acts on our toric variety, and H, since that also acts on it, and well, it can be proved that it acts nicely, and there is a quotient manifold, which is a complex manifold. So there is a theorem of Yoshida, which tells that there is equivalence between these two introduced categories, which says that in that kind of general definition which was given in the beginning, these spaces are all what we can obtain. So this tells that in realm of complex geometry, these are in some sense the most general spaces which can be associated to some kind of data of a fan and a compact torus. And there are well-known examples. So first of them is moment-angle complex manifolds. So they can be identified with the case when sigma our initial fan is a subfan of a fan of a simplex, namely just a cone on some m vertices. So let me show an example. Here m is equal to 4. So, and our fan sigma is a subfan of a cone on these 4 vectors, E1, E3, E2, and E4, which generate the basis of R4. And Q of sigma would be this complete simplicial fan in R2. Well, it's generated by the vectors A1, A2, A2, A3, A3, A4, and A1, A4. These are the maximal cones. So here sigma is a preimage of this Q of sigma. Then we should, for this picture, we should find some H. So we have a projection from R4 to R2, Q here, and we see that the kernel of this projection generated by these two relations, since A1 plus A3 is 0 and A2 plus A4 is also 0. So we have to find some complex subspace in C4 such that its projection on the real part gives us this subspace. And for instance, we can choose such H generated by this vector and this vector. So in this way, we obtain some moment angle manifold with sigma quotient by H, where this H is exponent of this linear subspace. Yeah, actually, it's also well, it's also a theorem that in this way you always construct some manifold which is isomorphic to the corresponding moment angle manifold corresponding to this to the simplicial complex underlying this span. Well, that's not hard. Well, this is a theorem. And another set of examples, which is also well known, is LVMP manifolds, and they correspond to the case when sigma is a subfan of a fan corresponding to Pm. So namely, it's a fan. This fan is different from this fan only by adding one more vector, which is equal to the minus sum of other vectors, and taking all the possible maximal cones on these vertices. Yeah, so these are namely the most famous examples which were known before Ishida introduced these complex manifolds with maximal torus action, but they generate, as you see, a more general family, since there is no restriction on the fan to be subfan of something very, very simple. Okay, so any element of this category admits so-called canonical foliation. So, and let me introduce you these foliations. So we have that our whole linear subspace GC is generated by the sum of H and H prime. So we can consider action of H prime, which is exponent of H prime, on our manifold M, since H prime sits inside of G, and it can be seen that this action is almost freely, namely that there is some neighborhood of identity in this group H prime, which acts freely on the whole space M. If the action of the group is almost freely, it always gives us a foliation on the whole manifold, by the leaves of this section, by the orbits of the section. So we call this foliation FH. Here's a picture. So we, on the whole toric variety V sigma, which sits above our manifold with maximal torus action, the whole algebraic torus X, and also gives some foliation F sigma on it. And the group H prime is equal to the quotient of the group JC by H, since this and since the groups are connected, and V sigma quotient by H is our manifold M. So obviously this action here goes down to this action here, and leaves of this foliation F sigma project down to the leaves of our canonical foliation. And actually, these canonical foliations may be described very generally for any manifold with some action or with some holomorphic action of a compact torus, and in some sense it's a defect of this action with respect to the complex structure. Okay. Well, any questions so far? Well, okay, if not, then I will proceed. So there is a very important notion for the foliations to be in some sense equivalent, and it's called transverse equivalence. So two foliations are said to be transverse equivalent if there exists another foliation M0 F0 and two maps F1 and F2, which are surjective submersions, and they should satisfy two conditions. First condition is that the preimage of any point under these maps is connected, and second, that the preimage of each leaf of any of these two of the foliations is a leaf of the foliation sitting above. So this transverse equivalence, for any foliation, we actually can associate so-called holonomy stack, and in the language of these stacks, this transverse equivalence actually says that the associated stacks are isomorphic. Okay, and we also introduce an equivalent of this transverse equivalence, which, well, analog of it inside of our category, such that our maps are stay inside of our category. So we say that two manifolds in C1 are P equivalent, namely principally equivalent if there exists another manifold in this category, and maps and morphisms F1 alpha 1, F2 alpha 2, satisfying two conditions. First of them is that the kernel of alpha is connected, and the second is that each of Fi is a principal kernel alpha I bundle. Okay, so then the claim is that P equivalence implies transverse equivalence. Actually, it's much stronger statement, but anyway, that's only what we would need. And there is a theorem which states that each complex manifold with maximal torus action is P equivalent to some moment ergo manifold. So this means that in a sense, if we want to say something about this stacks or these foliations up to this transverse equivalence, we can stay inside of the class of moment angle manifolds. Well, now I'll pass to basic homology. So what's this? It's a matter of homology of a base space inside of the case when the foliation is an actual fiber bundle. So we consider the following differential graded algebra of forms on M. Namely, these forms should satisfy two conditions: that they are trivial when we insert any vector field which is tangent to the leaf, and they are constant along the leaves. And these are actually two conditions which are necessary and sufficient in the case of a fiber bundle for a form on the total space to be a pullback of some form on the base space. And in the case when the foliation is induced by some action of group G on M, where here G is not necessarily compact torus. So, and if G is connected, then we can, in the same vein, introduce this differential graded algebra, where all the same satisfies, where for psi being any element in the algebra, and we insert and take lead derivative with respect to the vector field generated by this element of the algebra on our manifold M. Yeah, and the differential is the same drum differential which we have on our manifold, and then the homology of this differential graded algebra is a so-called basic homology. In our case, when they are induced by the action of a group, there are several quasi-isomorphic differential graded algebras which can compute the same homology, and one of them is a so-called Cartan model. So Cartan model is described as follows. So we take the tensor product of all forms on M with symmetric polynomials with values in G, and take all the invariants under the G action on this tensor product, and we consider some twisted differential, namely this is a Cartan differential, and it acts as follows. So the value of differential of some form omega sitting here on psi, which is an element of the algebra, is computed as follows. So the main thing about this Cartan algebra, Cartan model, is that it's quasi-isomorphic to initial basic DGA. And there is a very important claim which says that if two foliations are transverse equivalent, then the associated rings of basic homology are isomorphic. So because of the theorem above, that each complex manifold with maximal torus action is P equivalent to some moment angle manifold, it's enough to compute this ring in the case of moment angle manifolds. And so here's a theorem which is proved in our joint paper with Hiraki, Sida, and Taraspanov, which gives the full description of this ring in the sense of Davis-Januszkiewicz formula for cohomology of toric varieties. So, namely, if we have an element of this category C1, then its basic cohomology is isomorphic to the polynomial ring on M generators, which all of degree 2, quotient by two very well-known ideals. First of them is the Stanley-Reisner ideal, generated by those monomials which does not belong to the underlying simplicial complex of Fm. And the other is generated by these linear relations on Fn, which comes from this H prime, which is a kernel of our projection from G to G quotient by G, H prime. Okay, so, and here is the outline of the proof. So first important lemma is that we can compute our basic homology of this ring as cohomology of the following model. Namely, we take the Cartan model of the TM invariant form on the whole moment angular manifold Z sigma, and this algebra looks like the tensor product of polynomials on H prime tensor with TM invariance of Z sigma. Then, if we can consider the following diagram. So what happens here? N is our algebra, and it is actually isomorphic to tensor product of Cartan model for TM action on the whole moment angular manifold with R over polynomials with values in G prime, where G prime is a quotient of G by our H prime. And it's clearly seen since the Cartan model for Z sigma is S of J star tensor with this TM invariance, and we actually to produce N, which is given here, we just factor out this part. Well, then we have this square of maps where here the Cartan model stands, here R, and here are ring of polynomials. So this picture is actually resembles the standard picture of equivalent cohomology, and here would stand just the cohomology of manifold. Here would stand the equivalent cohomology. Here would stand the cohomology of EG, which is just R, and here would stand the cohomology of BG. But here, since our basic cohomology, they are not described as a natural cohomology on some manifold, we had to introduce some analog of that geometrical picture in the algebraic language. And so the best situation for the equivalent cohomology is equivalent formality, and it's actually what we prove in this case. We state that H star of N, the cohomology of this algebra, is a quotient of the cohomology of the algebra staying here by this polynomial ring. And the cohomology of a polynomial ring is the same since they all sit in degree 2, the generators. Okay, so this is our plan for the last 10 minutes to show the proof of this fact. And it's actually equivalent to the form of this isomorphism written above. The main step here is that this differential graded algebra standing for the Cartan model of TM action on the moment angle manifold, it is formal. And the exact of quasi-isomorphisms between this model and equivalent homology of the sigma can be introduced to respect the polynomial, the model structure of the polynomial ring corresponding to this torus. And this actually not the obvious result, and it's well, that's a corollary of result by Notbaum and Ray, where they proved in their paper of 2005 that the action, so this homology in the geometric interpretation is formal. So the geometric DGA standing for equivalent homology is formal. Okay, and then we apply the very famous corollary of Ellenberg-Moore spectral sequence, namely if we have some two DGAs and we have some morphism between them and two morphisms of modules over these DGAs which respect the structure of this map F, then it induces a morphism at the level of Tor algebras, and if each if F, G, and G prime are quasi-isomorphisms, then this induced map on the level of Tor algebras is an actual isomorphism. So now we have just to recap all this lemma above to show that there is a chain of isomorphism, namely that the Tor algebra, that such Tor algebra is isomorphic to this Tor algebra, and this Tor algebra is isomorphic to H star n. So to go a little bit deeper into the details, first we consider this Tor algebra in the middle, and we first notice that well, this transition is just rewriting of what's written here in terms of the Cartan algebra. Then we apply this corollary of result of Notbaum and Ray, use the formality, and from this formality and the chain of these quasi-isomorphisms, because of it we can apply lemma 3 to this chain of quasi-isomorphisms over this ring, and see that this Tor algebra is isomorphic now to the Tor algebra, where instead of this DGA model stands the equivalent homology. And now when it's when here we have only actual homology ring, we see that it's isomorphic to the zero Tor, which is just the tensor product of this guy and this guy over this model, which is a quotient which we're all looking for. And secondly, so we now went from here to here, and now to go from here to here, we use that we already proved that this Tor algebra is isomorphic to the zero Tor, and then it means that it's a tensor product of the homology of this algebra and this algebra here, and this is the homology we were looking for. So to make one more remark. It's essential to use. So the reason why we did not solve it in general for the complex manifolds with maximal torus action, but started with moment angle manifolds is that there was only known result for equivalent homology of moment angle manifolds introduced by Victor Buchstaber and Taraspanov, and there was no result like this for the complex manifolds with maximal torus action. Okay, so I guess I'll stop here and thank you for your attention.
Thank you very much. Let's thank the speaker. Are there any questions or comments? Okay, maybe I have one. The first two questions. The first question: what is a weak equivalence between categories?
Well, it means that well, not well. I would not speaking strictly, but namely, not every morphism kind of realizable. Morphism between panels is realizable as a morphism between manifolds, I guess, but nevertheless, there is some sort of equivalence.
Okay. Okay, let's, and the second question is about every beginning of your talk. Could you please open the first page of your notes?
Sure.
No, yes, this condition about sum of dimensions, is it necessary for the it's not that's sufficient condition, yes?
Yeah,
for
yeah, that's
maximality of
okay.
Okay.
Definitely, it's not.
You use and not you, but here using this condition, not maximality, yes?
Yes. So the definition of a manifold with maximal torus action, it's it doesn't mean that. So it doesn't mean that your action of a torus is just maximal. It's more than that.
Okay, thank you.
Yes, I can just comment that this is important. It's like this implies that the torus is a maximal torus in the automorphism group, but not the other way around. So that the condition is precisely this, or the dimension of the manifold, and that identity relating the dimension of the manifold and the dimension of the stabilizer. So this is a definition, and not that the torus is maximal in the automorphism group. Although, yeah, the term maximal may be misleading, but this is. Okay.
Okay, let's thank the speaker again. And we are ready.
Yeah.
Finish our conference.
Let me just say a couple of words. Yeah, first of all, thanks everyone for joining us in these difficult times. We had big plans for a major international conference around the end of the year in Moscow, but of course, yeah, that's and this international seminar for young researchers was supposed to be like a part of this bigger conference, but at the moment, this is the best that we can do. But anyway, we still have some plans for the next year. Maybe if the situation allows, we might have some bigger conference, both in Moscow and in Sochi in a year time. But we'll see how it will develop. Yeah. So, but for now, thanks everyone for joining us and for having all these wonderful talks.
Thank you, Taras. But it was wrong to say it was the best you could do. It was very good.
Okay, thank you, Tony.
It was a very good opportunity for the young people, but it was very close to the other. We need more warning before the conferences, Taras.
Well, yeah. But yeah, we had. I mean, we didn't want it to interfere with the other seminars that we had at, and other events. So we postponed it several times, and eventually, yeah, until it was too late, we needed to. We had some plans, some plans for organizing some meetings, so we had to do it in this year. So this.
It's uplifting to see all the good work these young people are doing.
Sure, absolutely.
Wonderful work. We are very lucky to have them all.
Okay, then thanks everyone.
Thank you.
Hope you see you again in the next meeting, maybe next year or
next week.
Next week. What will be next week? Christmas?
Oh, big conference on Christmas Day.
All right. Yes.
I forgot to tell you. Okay. Bye. Bye, Taras.
Yeah. Bye.
Thanks, organizers.
Bye.
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 Thanks, everyone. Bye.
Bye.
Okay, I will be ending the conference.